Linearizability versus serializability. Linearizability is easily confused with serializability. See serializability on page 251, as both words seem to mean something like can be arranged in a sequential order. However, they are two quite different guarantees, and it is important to distinguish between them. Serializability is an isolation property of transactions, where every transaction may read and write multiple objects, rows, documents, records. See single object and multi-object operations on page 228. It guarantees that transactions behave the same as if they had executed in some serial order, each transaction running to completion before the next transaction starts. It is okay for that serial order to be different from the order in which transactions were actually run. Linearizability is a recency guarantee on reads and writes of a register, an individual object. It doesn't group operations together into transactions, so it does not prevent problems such as write skew. See write skew and phantoms on page 246, unless you take additional measures such as materializing conflicts. See materializing conflicts on page 251. A database may provide both serializability and linearizability, and this combination is known as strict serializability or strong one-copy serializability, strong 1SR. Implementations of serializability based on two-phase locking. See two-phase locking 2PDEL on page 257, or actual serial execution. See actual serial execution on page 252, are typically linearizable. However, serializable snapshot isolation. See serializable snapshot isolation SSI on page 261 is not linearizable. By design, it makes reads from a consistent snapshot to avoid lock contention between readers and writers. The whole point of a consistent snapshot is that it does not include writes that are more recent than the snapshot, and thus reads from the snapshot are not linearizable. Roman 3. Strictly speaking, Zookeeper and ETCT provide linearizable writes, but reads may be stale, since by default they can be served by any one of the replicas. You can optionally request a linearizable read. ETCT calls this a quorum read, and in Zookeeper you need to call sync before the read. See implementing linearizable storage using total order broadcast on page 350. Relying on linearizability. In what circumstances is linearizability useful? Viewing the final score of a sporting match is perhaps a frivolous example. A result that is outdated by a few seconds is unlikely to cause any real harm in this situation. However, there are few areas in which linearizability is an important requirement for making a system work correctly. A system that uses single leader replication needs to ensure that there is indeed only one leader, not several split brain. One way of electing a leader is to use a lock. Every node that starts up tries to acquire the lock, and the one that succeeds becomes the leader. No matter how this lock is implemented, it must be linearizable. All nodes must agree which node owns the lock. Otherwise it is useless. Coordination services like Apache Zookeeper and ETCT are often used to implement distributed locks and leader election. They use consensus algorithms to implement linearizable operations in a fault-tolerant way. We discuss such algorithms later in this chapter. In fault-tolerant consensus on page 364. Roman 3. There are still many subtle details to implementing locks and leader election correctly. See for example the fencing issue in the leader and the lock on page 301, and libraries like Apache Curator help by providing higher-level recipes on top of Zookeeper. However, a linearizable storage service is the basic foundation for these coordination tasks. Distributed locking is also used at a much more granular level in some distributed databases, such as Oracle Real Application Clusters (RAC). RAC uses a lock per disk page, with multiple nodes sharing access to the same disk storage system. Since these linearizable locks are on the critical path of transaction execution, RAC deployments usually have a dedicated cluster interconnect network for communication between database nodes. Uniqueness constraints are common in databases. For example, a username or email address must uniquely identify one user, and in a file storage service there cannot be two files with the same path and file name. If you want to enforce this constraint as the data is written such that if two people try to concurrently create a user or a file with the same name, one of them will be returned in error, you need linearizability. This situation is actually similar to a lock. When a user registers for your service, you can think of them acquiring a lock on their chosen username. The operation is also very similar to an atomic comparand set, setting the username to the ID of the user who claimed it, provided that the username is not already taken. Similar issues arise if you want to ensure that a bank account balance never goes negative, or that you don't sell more items than you have in stock in the warehouse, or that two people don't concurrently book the same seat on a flight or in a theater. These constraints all require there to be a single up-to-date value, the account balance, the stock level, the seat occupancy that all nodes agree on. In real applications, it is sometimes acceptable to treat such constraints loosely. For example, if a flight is overbooked, you can move customers to a different flight and offer them compensation for the inconvenience. In such cases, linearizability may not be needed, and we will discuss such loosely interpreted constraints in timeliness and integrity on page 524. However, a hard uniqueness constraint, such as the one you typically find in relational databases, requires linearizability. Other kinds of constraints, such as foreign key or attribute constraints, can be implemented without requiring linearizability. Notice a detail in figure 9-1. If Alice hadn't exclaimed the score, Bob wouldn't have known that the result of his query was stale. He would have just refreshed the page again a few seconds later, and eventually seen the final score. The linearizability violation was only noticed because there was an additional communication channel in the system, Alice's voice to Bob's ears. Similar situations can arise in computer systems. For example, say you have a website where users can upload a photo, and a background process resizes the photos to lower resolution for faster download thumbnails. The architecture and data flow of this system is illustrated in figure 9-5. The image resizer needs to be explicitly instructed to perform a resizing job, and this instruction is sent from the web server to the resizer via message queue. See chapter 11. The web server doesn't place the entire photo on the queue, since most message brokers are designed for small messages, and a photo may be several megabytes in size. Instead, the photo is first written to a file storage service, and once the write is complete, the instruction to the resizer is placed on the queue. Figure 9-5. The web server and image resizer communicate both through file storage and a message queue, opening the potential for race conditions. If the file storage service is linearizable, then this system should work fine. If it is not linearizable, there is the risk of a race condition. The message queue steps 3 and 4 in figure 9-5 might be faster than the internal replication inside the storage service. In this case, when the resizer fetches the image step 5, it might see an old version of the image, or nothing at all. If it processes an old version of the image, the full size and resized images in the file storage become permanently inconsistent. This problem arises because there are two different communication channels between the web server and the resizer, the file storage and the message queue. Without the recency guarantee of linearizability, race conditions between these two channels are possible. This situation is analogous to figure 9-1, where there was also a race condition between two communication channels, the database replication and the real-life audio channel between Alice's mouth and Bob's ears. Linearizability is not the only way of avoiding this race condition, but it's the simplest to understand. If you control the additional communication channel, like in the case of the message queue, but not in the case of Alice and Bob, you can use alternative approaches similar to what we discussed in Reading Your Own Rights on page 162, at the cost of additional complexity. Implementing linearizable systems. Now that we've looked at a few examples in which linearizability is useful, let's think about how we might implement a system that offers linearizable semantics. Since linearizability essentially means behave as though there is only a single copy of the data, and all operations on it are atomic, the simplest answer would be to really only use a single copy of the data. However, that approach would not be able to tolerate faults. If the node holding that one copy failed, the data would be lost, or at least inaccessible until the node was brought up again. Roman 4. Partitioning, sharding a single leader database so that there is a separate leader per partition, does not affect linearizability, since it is only a single object guarantee. Cross-partition transactions are a different matter. See distributed transactions and consensus on page 352. The most common approach to making a system fault-tolerant is to use replication. Let's revisit the replication methods from chapter 5 and compare whether they can be made linearizable. Single leader replication potentially linearizable in a system with single leader replication. See leaders and followers on page 152. The leader has the primary copy of the data that is used for writes, and the followers maintain backup copies of the data on other nodes. If you make reads from the leader, or from synchronously updated followers, they have the potential to be linearizable. Roman 4. However, not every single leader database is actually linearizable. either by design, for example because it uses snapshot isolation or due to concurrency bugs. Using the leader for reads relies on the assumption that you know for sure who the leader is. As discussed in The Truth is Defined by the Majority on page 300, it is quite possible for a node to think that it is the leader, when in fact it is not, and if the delusional leader continues to serve requests, it is likely to violate linearizability. With asynchronous replication, failover may even lose committed writes. See handling node outages on page 156, which violates both durability and linearizability. Consensus algorithms. Linearizable. Some consensus algorithms, which we will discuss later in this chapter, bear a resemblance to single leader replication. However, consensus protocols contain measures to prevent split brain and stale replicas. Thanks to these details, consensus algorithms can implement linearizable storage safely. This is how Zookeeper and ETCT work. For example, multi-leader replication. Not linearizable systems with multi-leader replication are generally not linearizable because they concurrently process writes on multiple nodes and asynchronously replicate them to other nodes. For this reason, they can produce conflicting writes that require resolution. See handling write conflicts on page 171. Such conflicts are an artifact of the lack of a single copy of the data. Leaderless replication. Probably not linearizable for systems with leaderless replication. Dynamo style. See leaderless replication on page 177. People sometimes claim that you can obtain strong consistency by requiring quorum reads and writes W plus RN. Depending on the exact configuration of the quorums, and depending on how you define strong consistency, this is not quite true. Last write wins conflict resolution methods based on time of day clocks. For example, in Cassandra, see relying on synchronized clocks on page 291, or almost certainly non-linearizable, because clock timestamps cannot be guaranteed to be consistent with actual event ordering due to clock skew. Sloppy quorums, and hint at handoff on page 183 also ruin any chance of linearizability. Even with strict quorums, non-linearizable behavior is possible, as demonstrated in the next section. Intuitively, it seems as though strict quorum reads and writes should be linearizable in a dynamo-style model. However, when we have variable network delays, it is possible to have race conditions, as demonstrated in Figure 9-6. In Figure 9-6, the initial value of x is 0, and a writer client is updating x to 1 by sending the write to all three replicas n equals 3, w equals 3. Concurrently, client A reads from a quorum of two nodes R equals 2 and sees the new value 1 on one of the nodes. Also concurrently with the write, client B reads from a different quorum of two nodes and gets back the old value 0 from both. The quorum condition is met W plus RN, but this execution is nevertheless not linearizable. B's request begins after A's request completes, but B returns the old value while A returns the new value. It's once again the Alice and Bob situation from Figure 9-1. Interestingly, it is possible to make dynamo-style quorums linearizable at the cost of reduced performance. A reader must perform read repair. See read repair and anti-entropy on page 178 synchronously before returning results to the application, and a writer must read the latest state of a quorum of nodes before sending its writes. However, RIAC does not perform synchronous read repair due to the performance penalty. Cassandra does wait for read repair to complete on quorum reads, but it loses linearizability if there are multiple concurrent writes to the same key, due to its use of last write wins conflict resolution. Moreover, only linearizable read and write operations can be implemented in this way. A linearizable compare and set operation cannot, because it requires a consensus algorithm. In summary, it is safest to assume that a leaderless system with dynamo-style replication does not provide linearizability.